All right. So everything should be graded on Canvas, with the exception of kind of having the opportunity, if you missed any of those online quizzes, to be able to go back and do those if you have any kind of zeros in there for ones that you missed. And then I'll kind of at the end of the day get those factored in. I think so. The average after I graded the short answer part on the exam was right around, I was thinking it's like 75.5. The average grade in the class right now is close to a 79, 78, 79, somewhere in between there. Now, the grade that you see reflected, so I kind of have the weights for all the different categories as well as the exam now on there. I'm treating the exam as though it was everybody's best exam, right? So I weighted it as 30%. Obviously, as we take the other exams, that's going to change for some of you, especially if you didn't do as well in the first exam. It's probably more likely you do better on the second and third, and then that goes from being weighted 30% maybe down to 10. So it's kind of worst case scenario for you if you didn't do well in the exam. That's kind of the grade that's being displayed. Also, I dropped the lowest of each homework type. Obviously, we don't have a bunch of homework in there yet, so I haven't dropped anything. So if you missed one, but you do the rest of that assignment type, that's going to be one that gets dropped. So it's kind of a worst case scenario grade right now if you have any missing assignments or you didn't do as well in the exam. Okay. If you have any questions over any kind of grading on I got the Excel number 2 as well as the short answer, please reach out, let me know. I think a couple of you, there was a few where I had to maybe it was missing, and so I assumed that you just didn't upload something because you didn't know the answer. So I kind of gave a 0 if you didn't upload anything for the short answer portion. There's a Learn Smart assignment you need to get done by the end of the day as well today, so get those easy points. Chapter 6, the first Connect assignment, the next Connect assignment is up there as well. If you want to start working on that, it's things that we went over Wednesday and today, you can probably work through the first few questions, probably not a whole, too many of them. But as we kind of continue to work through material, we'll be able to complete more and more of that. All right. Any questions for me before we get started here? Double check the chat. Pops up over here when I open it. All right. So I think where we left off, I told you I'd tell you a little story to kind of lead into things. So there's this guy, and we started talking about the normal distribution. Oh, I didn't want to go from that slide. We started talking about the normal distribution. We said that there's this guy, Gauss, who really was kind of one of the main people that kind of discovered this normal distribution, or what we sometimes will call a Gaussian distribution, or a bell curve. Right? So he's this brilliant guy. Kind of one of the anecdotes about him is that when he was a kid, he got in trouble in class. He was really young. The teacher in elementary school told him, go over in the corner, count from 1 to 100, add up all those numbers, right? So 1 + 2 is 3, + 3 is 6, and go all the way to 100. So he comes back in a matter of seconds, and the teacher's like, there's no way that you've done this. She gives him the answer, and lo and behold, the answer is correct. So how did he do it? Well, if we think about it, what's 1 + 100? 101. What's 2 + 99? 101. What's 3 + 98? 101. So you can continue to do that all the way down to 50 and 51. Those add up to 101. So you'd have 50 pairs that add up to 101. Multiply those two, and you'd have 5,050. Right? So this kid, when he was a kid, came up with this in his head. Really smart guy. And there's an actual formalized equation that you can do that for any numbers. So if you want to add up from 1 to 1,000, your n is 1,000. You plug it in here, you'd actually get what those numbers would add up to. Right? That has nothing to do with what we're going to talk about today, which is the normal distribution, which we said pops up in a lot of these. What kind of Gauss and others notice is it pops up in a lot of biological markers, right? Height, human weight, human performance, rainfall, temperature. A lot of these things that we see in nature occur, and their distribution follows a normal distribution. So if I was to record every single person's height in the United States and then make like a histogram of it, it would kind of look like this nice normal distribution. Right? So we said any normal distribution has this density function, right, which we're not going to necessarily be using. It's going to be floating around in the background. But two things that were part of this was the mean and the variance. So we can see a normal distribution for tons of different variables, right? In fact, the one that we kind of started out saying was human height, males and females, both follow a normal distribution, but one of them has a lower mean. So they still have the same density function. It's just that the mean for female height would be different than the mean for male height. And what that's going to do for us, and I think we talked about this last class, I'll return to it in a second. But what that's going to do is if we have normally distributed variables, they have the same variance but different means, all that's going to do is shift that normal distribution to the left or right, right? So you can kind of imagine maybe this gray line here, maybe that's the distribution for height for women. Distribution for height for men is also normal, but it has a slightly higher mean, maybe mu2 here, okay? So one thing just to kind of revisit, I believe we did this, said this at the end of last class, but an important thing to remember about the normal distribution is it's symmetric. So essentially if we were to take the mean, which is equal to the median is equal to the mode, it would exactly split that normal distribution in half and it would kind of fold on top of itself, right? We also said it's defined by the mean and the variance. We already kind of thought about how the mean impacts that normal distribution, just shifts it along the x-axis. Now the variance is going to affect the height of that normal distribution, okay? So if we think about a normally distributed variable, let's say it has the variance of 5, okay? If we looked at another distribution that has the same mean, so notice these have the same mean, but the second distribution has a higher variance, right? Instead of 5, the variance is 10. What that means is the data is more spread out, right? Or the values that we could see this variable take on, there's a wider range of variables, or values that are further from the mean, are more likely, right? If I have a higher variance for that variable, then seeing values from the mean would be more likely, okay? Now, how does that play out kind of on this graph? Well, if we think about this y-axis kind of representing our probabilities, notice when I look at values that are further from the mean out here, for the distribution that has a higher variance, the likelihood of seeing those values is greater than the distribution that has a lower variance. And that's because higher variance, values further from the mean are more likely, or said differently, values near the mean should be more likely when I have a low variance. So if we look here, when we have this lower variance, notice the values right around the mean are more likely for that distribution that has a lower variance, okay? And we can kind of imagine if I go to even higher variance, the values near the mean become less likely, the values further from the mean become more likely, right? So a higher variance essentially squishes my normal distribution, or it flattens it out, right? The higher the variance, the flatter this distribution gets. The lower the variance, the kind of more peaked or higher this distribution gets, okay? And that's the reason, because what the variance is telling us is how likely it is we see values near the mean or further from the mean, okay? Any questions on that? Is that kind of making some sense to people? Okay with that? So if I look here and I have the distribution of male and female height, if I don't give you the numbers for what the mean and the variance are, just looking at this picture, you can tell. So which of these groups has a higher mean? Well, if we look at kind of where that normal distribution would get split in half, I guess what 70, 71 would be kind of the average for male height. 64, 65 looks like the average for female height. So we would say kind of this, they're both normally distributed, but male height has a slightly higher mean. Which of these has a higher variance? Male or female height distribution? Yeah, right? The higher the variance, the flatter that distribution is going to get, or the flatter that curve. So we notice which one is kind of flatter here, or kind of not as peaked. That would be male height. So we see much more variation in male height than we do female height, but they're both nice normally distributed variables, okay? There's another thing we want to remember. When we're dealing with a uniform distribution, kind of it was just this rectangle that had an area of 1, right? But really the reason why is because it's the area under the curve is 1. It's just for a uniform distribution, our curve was a flat line. So now we can think about this area, under this curve should be 1, right? But we can start to think about kind of breaking that down, right? So I'm going to tell you something by the end of the class. Well, I'll kind of hopefully prove it to you using some z-scores and this table that we're going to look at. But for now, just believe what I'm saying, right? So if we were to go one standard deviation below and one standard deviation above the mean for any normally distributed variable, if I go one standard deviation above and below, the probability that I see that variable, if I selected like one person at random, if we're dealing with an example, we're looking at, say, human height. If I chose one person at random, the probability their height is within one standard deviation above or below the mean, the probability will always be about 68%. If I then go two standard deviations above and below, the probability I see their height be somewhere in between two standard deviations above and below the mean is about 95%. Now this kind of makes sense. If I'm just increasing the number of possible values I could see, right? If I go one standard deviation away, I don't have near as many values in this range as I do when I go two standard deviations above and below the mean. So as I kind of think about going more and more standard deviations further from the mean, the probability I see something in between those two values should be getting larger. So if I go to 3 standard deviations above and below the mean, well, at that point, I'm almost at 100%, right? Or almost at that probability of 1. And that kind of makes sense, right? Let's say, let's say we'll do male height. Let's say the average is 71 inches. And I don't know, let's say that the standard deviation is 3 inches, right? If I were to go 3 standard deviations above and below, so if the standard deviation is 3 standard deviations would be 9. So if I said, what's the probability if I chose someone at random, they're in between 71 plus 9, so 80 inches, and 71 minus 9, so 62 inches, right? Well, really what I'm saying there, what's the probability that if I chose a male at random, they're between 5'2", right? And what would be, what did I say, 80? So it would have to be 72, so 6'8". What's the probability between 6'8" and 5'2"? Pretty high, right? I mean, there's not many people who are taller than 6'8". There's not a whole lot of kind of men that are short. Now there are some, right? We haven't included every possible value here, but you know, we've kind of widened that range to be pretty likely we see someone within that many standard deviations. Okay. So how am I getting these values, right? I'm not going to expect you to kind of have these memorized, right? We actually can get these. In fact, we don't need to just do 1, 2, and 3. I could find what's the probability that's in between 1.25 standard deviations above and below the mean, right? So how are we going to do that process? Well, the first thing we want to think about is we have these normally distributed variables. So this random variable x, the way we'll say it's normally distributed is kind of writing this, you know, x is normally distributed, n, and here's its mean, and here's its variance, because those are the two things that would change, like shift our distribution or flatten or kind of make it more peaked. Okay? Well, if we think about if we had a variable that was normally distributed and had a mean of 0 and a variance of 1, we go back to this equation, it would make things a lot easier if we're trying to, say, integrate that function. So if I can get back there, there we go. Right, if I plug in a 1 here, then it's just 1 over 2 pi. Plug a 1 in here, it's just 2. Plug in 0 here, now I've just got x. So it would make that a little bit easier to deal with. And what people have already done is, actually I'll go to the board first. So if I had that, there we go, normally distributed variable, and it had this mean of 0 and variance of 1, I could then start to think about, okay, what's the probability that I saw something below this value, right? Or what we said before, what that really is saying is like a cumulative density function, right? What's the probability I see A or anything below it? Now, if I have a mean of 0 and a variance of 1, to find the probability I see A or anything below it, I can actually use, oh, why is it not, why is it blank? Let's try reopening it, I guess. Where's this table? There we go. There we go. If it has that mean of 0, variance of 1, I can start to look up values from this table, and the way that we would read this table, and I'll review it here in a second, is -3.81. The probably I see something below that value would be 0.001. So this table essentially gives us these cumulative density functions for certain values of x, right? But only if that variable x has a mean of 0, variance of 1. So what if we're dealing with a variable that doesn't have that? Well, hopefully by the end of class, we'll kind of talk about how we can convert that variable. Let me see, where was that? We'll talk about how can I convert this variable that doesn't have a mean of 0 and a variance of 1 into a variable that has a mean of 0, variance of 1, and then use that table to find the probabilities I'm interested in. Right? That's kind of the end game of what we're going to do. So if I do have this distribution that has a mean of 0 and a variance of 1, right, we're going to call those values kind of z-values, and we'll talk about how we convert a variable that doesn't have mean 0, variance 1 into a variable that has mean 0, variance of 1, and we'll call those kind of z-values instead of x-values. Okay? So z-values come from having a random variable that's normally distributed with a mean 0, variance of 1. Right? What these z-values will represent then is the number of standard deviations away from the mean that whatever value you're looking at is. So if we think about it here, if I had these z-values and I know they're normally distributed with a mean 0, variance of 1, well, what would be one standard deviation away from the mean? Well, if the mean is 0, being one standard deviation away from the mean, when the variance is 1, so if I have a variance of 1, what's the standard deviation? Just the square root of that? Well, the square root of 1 is 1. So if I go one standard deviation above the mean, it would be 0 plus 1, right? So just a z-score of 1. So if I'm one standard deviation above the mean with a standard normally distributed variable, which is standard normally distributed refers to that it has a mean of 0, variance of 1, that z-score of 1 represents I'm one standard deviation above the mean. But what if I wanted to go 2 standard deviations below the mean? Well, if the standard deviation is 1, 2 below would be subtracting 2 times 1 from 0, which would be -2. So these z-scores, or these values from a standard normally distributed variable, really just represent the number of standard deviations away from the mean that I am. Okay? That's the interpretation of these z-values. Okay? So how do I take an original variable x and turn it into a z-value, right? Or what we'll call a z-score. Okay? So the way I do this is I start out with some normally distributed variable. It has its own mean. It has its own standard deviation. If I'm interested in a specific value for x and say, what's the probability that someone, say, less than 70 inches tall? I would take that value for x, which is 70. I would subtract the mean height, divide by the standard deviation, and now I've converted that value of 70 into a z-score. Well, once I have a z-score, I can find the probability I saw that z-score or anything below it by using that table. And I'll talk a little bit more how we use the table here in just a second. But that's kind of where we're going. So once I convert these into z-scores, now, just like I said in the previous slide, the z-score represents the number of standard deviations away from the mean that value for x was. So once I turn 70 into a z-score, that z-score represents how far away 70 inches was from the mean height. Okay? Now, if we think about what would the mean have a z-score of? Well, if I plug in the value for x, which would be the mean, it had to have the mean minus the mean. So our mean will always be a z-score of 0, which makes sense, because how many standard deviations away from the mean is the mean? 0, right? It is the mean. It's no standard deviations away from the mean. Also, we can think about the sign kind of tells us whether or not we're above or below. If I have a z-score of +2, that means I'm 2 standard deviations above the mean. If I have a z-score of -3.5, that means I'm 3.5 standard deviations below the mean. So the sign kind of tells us what side of the mean we're on. And then kind of the number tells us how many standard deviations away we are. So these z-scores represent a standard normal distribution that has a mean of 0, variance of 1. But why does that always work? So I'll kind of show you, I'll kind of prove to you that if we use this formula and we were to take every single possible outcome for x and convert them into z-scores, we can see that they'll always have a mean 0, variance of 1. So I'll give you a quick little set of values, and I'll hopefully kind of prove this to you. Right? So we've got, let's say 2, 4, 6, and 8. Right? So this is my variable x. If I find the mean of x here, what would I do? Well, I'd add these values up, divide by the number of values I have. So 2 plus 4 plus 6 plus 8 is 20, divided by, I have 4 values, so my mean for x would be 20 over 4, or 5. Right? What would my variance for x be? Well, I'm not going to go through and write down all the intermediate work, but what would we do? Well, we'd say take 2 minus the mean of 5, so negative 3, square it, so that'd be 9. I'll just do this temporary. 9, 4 minus 5, because that's the mean, squared, 1, 6 minus 5 squared is 1, 8 minus 5 squared is 9. Add these values up. I'll treat this as a population just to make it easy. So we add these up and still divide by the number of numbers we have, which is 4. This adds up to 20. 20 over 4. I'm giving you kind of a weird example where this variable x, has a mean and a variance of 5. Okay? So if the variance is 5, the standard deviation would just be the square root of that. So square root of 5. Okay? So I'm now going to convert every possible outcome I could see here into a z-score. And then I'm going to find the mean and the variance of that z-score. Right? So for the first one, right, what would I do? 2 minus the mean, divide by the standard deviation. So 2 minus 5 is negative 3, divide by the standard deviation. Turn the next one into a z-score. Take that value for x4, subtract the mean of 5, divide by the standard deviation. I get 1 over this, actually negative 1, over the square root of 5. Turn this one into a z-score. 6 minus 5, divide by the standard deviation. 8 minus 5, divide by the standard deviation. If I look at my new variable z, what's the mean? Well, if I add these up, notice these cancel out, these cancel out. I have a mean for this z-score, which will be 0. Right? I then can go through, well, now that I have the mean of this variable, what's the standard deviation, or what's the variance? We'll do the variance first. Well, I would take this value, subtract the mean, square that deviation, then add this value minus the mean squared, and I keep doing that. So if I subtract 0, it's really just this value, right? So if I square this, I get what? 9/5, because negative 3 squared is 9, the square root of 5 squared is 5. I square this value, I get 1/5. I square this value, I get 1/5. I square this value, I get 3/5. Nope, not 3/5. 9/5. Right? So if I then look at this and I add these up, I'll get 20 over 5. But I still need to define the standard deviation, divide by the number of numbers I had. I have 4 numbers, so 20 over 5 is 4. Divided by 4, I get a variance of 1. If I have a variance of 1, what's the standard deviation? Well, it's also 1. Right? So this is just kind of a nice, like a quick, if I had a small, obviously for a continuous random variable, we don't just have 4 values. But even with just 4 values, this kind of shows you, if I use that equation and convert this variable x into a z-scores, these z-scores will always have a mean of 0 and a standard deviation or variance of 1. Okay? Any questions on that? And you're not going to have to like go through and do this by hand every single time. This is just kind of some support to kind of prove to you that that's what's going on. All right. Okay. So if we're okay with that, I can convert any variable that's normally distributed into z-scores. So if I think about this, if I look at my normally distributed variable x, if I convert the mean into a z-score, well, I would have the mean minus the mean divided by the standard deviation. Well, it doesn't matter. Mean minus the mean is 0 there. So my z-score for the mean would always be 0. If If I go 1 standard deviation above the mean, I should have a z-score of 1 because that's the interpretation of the z-score. And if I go 3 standard deviations below, I should have a z-score of -3. So why can I map this out? Well, let's think about it. So I have my z-score equation, which is just take the value I'm interested in, x, subtract the mean, and divide by the standard deviation. Right? Well, let's say the value for x that I'm interested in is 1.2 standard deviations above the mean. So if this is the value I'm interested in, when I convert it into a z-score, I would have the mean plus 1.2 times the standard deviation minus the mean divided by the standard deviation. Well, the mean minus the mean, this cancels. 1.2 times the standard deviation divided by the standard deviation, that cancels. And so my z-score for a value that is 1.2 standard deviations above the mean will end up being 1.2. Right? So that's why we could map out all those, different standard deviations away from the mean. We can map those all out onto their z-scores pretty easily. Okay? Now, in practice, you're not going to be told it's 1.2 standard deviations above the mean. You're going to see the value of, not z, you'll see like a value like 70. You don't know how many standard deviations away from the mean it is, but you know that once you convert it into a z-score, that z-score will tell you how many standard deviations away from the mean that value of 70 is. Is this kind of making some sense? Any questions? Okay, so I'm trying to kind of set this up, maybe go a little bit more in detail than I usually would, because we'll be using this normal distribution and this idea of z-scores for a long time, most of the rest of the semester, right? We'll actually complicate it some. So I want to make sure we have a good kind of base and foundation here. So let me make sure there's no, okay. So why are we finding these z-scores? Well, because for a lot of things, we might want to know, okay, for this continuous random variable, what's the probability that we see the outcome be between values a and b? Now, we did this for the uniform distribution because we had a nice, easier density function. But for the normal distribution, I don't want to have to integrate from a to b, right? So if I have, just for the recorded video, I'm gonna, while I'm talking, pull this up right now. So if I had some normally distributed variable x, it doesn't have a mean of 0 and a variance of 1, I know the function that gives me that line. That was that messy probability density function. I could integrate from a to b that function and find the area under the curve, which would be the probability it's between a and b. But I don't want to have to do that every single time, right? It's a lot easier to convert these values into z-scores and then be able to use that standard normal table where all that integration is already done for us. Okay? So someone's already done it for us, so let's take a look at that table, right? So let's say I wanted the probability that a z-score, right? Let's say I'm interested in some value, I started out with some variable x, but now I want to kind of give you a little bit more idea of after I convert that value of x into a z-score, how do I use the table then? Okay? So let's say I had some value, I convert it into a z-score, and it's negative 1.29. So it's 1.29 standard deviations below the mean. What was the probability I saw that z-score of negative 1.29 or anything below it? Right? Well, this is just a cumulative density function, right? The probability I see negative 1.29 or anything below it. So how do I use the table to find that probability will always be 0.0985? If I have a z-score of negative 1.29, the probability that I saw something that was 1.29 standard deviations below the mean or anything further from it will always be 0.0985. So how can I find that? Now, this is why I said it probably helps to have a table in front of you. This is kind of small. I'll do my best. I'll probably switch over to the table so I can zoom in here, but I have some stuff in the slides that I think is helpful. So I've got negative 1.29. I want to find the area to the left of it, or the probability I saw that z-score or anything less. What I do is I look up the first decimal point from my row heading. So I go negative 1.2. I then look up that second decimal using these column headings. So I go negative 1.2 9, right? So negative 1.2, whoops, negative 1.29. I then go to where that row and column heading kind of would meet. And I find that the probability onto the left of negative 1.29 is this 0.0985. So these values in the middle of the table are probabilities, and they're telling me the probability that whatever z value I looked up, that I saw that z value or anything to the left or anything less than that. Right? So that's how we read these tables. Any other questions before I keep moving here? Okay with this? So what if I looked up the probability of being less than or equal to positive 1.29? Well, it's the exact same kind of way we read the negative side of the table, right? Positive 1.29, that probability is 0.9015. So also something that's kind of helpful when you're using these tables, if you have like a pencil or something, like lightly kind of going over in your row and then down to the column to make sure that you're grabbing the right value, right? Because it is a little bit kind of tricky. I might end up going to like the row above or below sometimes. So using something to kind of trace like a pencil or even your finger kind of is helpful in doing that. Okay, so this is how we use the table to look up those probabilities. I think what I want to say here is, what if I wanted the probability of being, so I could find the probability I'm less than or equal to positive 1.29. When we look that up here, 0.9015. What did I have? It should be a 5, not an 8. Sorry. So we can stay consistent and kind of match this up, right? So 0.9015, right? So what's the area to the right? Or what's the probability I see 1.29 or greater? Just be, what's the area under the curve? 1. If this blue area is 0.9015, what's the white area? Just 1 minus that, right? So I can't get the probability of being greater than certain values from the table, but I can always find the probability that I'm less than that value. And then because I know the area under the curve is 1, I then can just subtract whatever value to the left is from 1, and it would give me the area to the right. So kind of using our complement rule there, right? You can do that. But when we actually use these tables, these probabilities are always, and the table kind of reminds you, it's always telling you the area to the left. Okay? So if you want the area to the right or the probability it's greater than that value, you'll have to do 1 minus. Okay? Let's keep going. So I can look up these different z values, and these will just be some we see a lot. You could look all these up and find the probabilities to the left. Now notice they're kind of benchmarked. This is about 90%, about 95, 97.5, 99, 99.5. So we'll see these z-scores kind of pop up quite a bit. Okay. I already kind of mentioned this, with the idea there being, if I look up the probability I'm less than 1.29, I want the probability that I'm greater than, just 1 minus. Also, notice I keep the equalities on here. Remember why, something I said from last class, why it doesn't matter if we keep the equality on both sides. What's the probability of any one value? Probability of any one value is 0. Right? So we said it's kind of weird when we're dealing with a truly continuous random variable. The probability that I'm greater than 1.29 is actually also the same as the probability I'm greater than or equal to 1.29. So it kind of makes our life easier. If we forget the equality or include it or don't include it, it won't change our answers. Okay? Another thing I want to mention here is that our normal distribution, where are we at in time? Oh, okay, is symmetric, right? So if I look at that mean of 0 for my z-scores, the probability that I see something to the left of the mean or the right of the mean of 0 is 0.5. So if I look up any z-score that's negative, so let's say I turn this into, these other ones don't show up as well, but my markers always keep dying. I must use this one. Let me see if I have another black marker here. I do. So if I look at these z-scores, and I have that mean of 0, right? If I look up any negative z-score, negative anything, what do I know the area to the left of it has to be less than? Well, what's the area to the left of 0? I just said if it's symmetric, right, 0.5. So if this area is 0.5, if I go over any amount, right, to any negative z-score, the area to the left of it has to be less than 0.5. Similarly, if I go to any positive z-score, and I want the area to the left, I know that that area has to be greater than 0.5, right? Because the area to the left of the mean, or left of 0, is 0.5. Well, I want an area that's larger than that, right? If I just draw this out every time, I can kind of be reminded, oh yeah, this area definitely has to be greater than 0.5, or this area has to be less than 0.5. So if we look at that table, go back here, notice when I'm looking at the negative side of the table, all these probabilities are less than 0.5. In fact, well, I have this pesky thing down here. Hold on. Let's get rid of this footer for a second. Notice when I go to 0.00, the area to the left of that is 0.5. Right? And then when I look at the positive values, all the probabilities are greater than 0.5. Right? Okay. All right, so we got that out of the way. So what if I wanted the probability that a z-score is greater than or equal to negative 2.53? So this is where, once you know what you're looking for, every single time, this is what I would suggest doing, okay? I would suggest drawing out your normal distribution, plotting that z-value, and thinking about what that probability is kind of bounded by. So I already forgot what it was. Was it the probability that's greater than negative 2.53? Anybody want to check? It is? Okay, just making sure. I didn't want to do a different example. So I want the probability that I see a z-score of negative 2.53 or anything greater. So right away, what do I know this area has to be larger than? 0.5. Because the area to the right of that mean of 0 is 0.5. I want an area larger than that. Now this really helps me because when I look this value up in the table will tell me the area to the left. And so if I automatically draw this out and remember, oh yeah, this has to be greater than 0.5, it'll prevent me from forgetting to then subtract that from 1, right? So we'll go to that table. No, these are the slides. We'll go to the table, right? We'll look up negative 2.5 and then go over to 2.53. So that probability is 0.0057. Which means the area that I want, or the area to the right, is just 1 minus that, okay? Any questions on that? Shouldn't be too bad. So if I look at these answers right away, I actually didn't even really need to look this one up. Well, I'll explain to you why you didn't have to look this one up if you had these possible answers. First of all, which of these can I get rid of right away? C, right? I'm looking for a probability. The very lowest it could be is 0. Right? I can also get rid of B because we said this probability has to be greater than 0.5. Now, why could I guess, I mean, if we want to get real theoretical, we're probably not familiar enough to know that we can rule out A yet. But if the probability that I was to the right of negative 2.53, if I'm thinking about what z-score would have an area to the right of almost 0.5, it would have to be something really, really close to the mean, right? If the area is just barely over 0.5, it'd have to be something that was like 0.1 standard deviation away. We've got something that's negative 2.5 standard deviations. And now this is where I said we're probably not familiar enough yet, but if I see something 2.5 standard deviations away from the mean, the probability I saw something that far away from the mean or any further is only 0.0057. Like, it's very unlikely to see things that are more than 2 standard deviations away from the mean. And so, like I said, maybe we're not familiar enough to know that we could have ruled A out yet. But if we kind of thought about what would that z-score have to be close to, have to be really close to 0, right? And it's not, it's negative 2.53, right? When we look at z-scores, I mean, generally we're thinking about things from negative 3 to 3. We don't usually see things that are more than 3 standard deviations above or below the mean, okay? And if we do, it means it was very unlikely, okay? So if I wanted the probability that I'm less than negative 2.53, these would be a lot easier because it's literally what we did in the last problem, except I can just look it up in the table and now I'm done, right? Because I wanted the area to the left. That's what the table tells me. That's a lot easier. Now, one thing I want to point out here, I think we're good on time, right? So yeah, I need to go through this before we stop, right? So let's think about a couple things. If I have that value of negative 2.53, and I know this area is 0.0057, that's the value we looked up, what's the probability that I see something to the right of positive 2.53? Well, if this is a symmetric distribution, it folds on top of itself if I fold it across the mean. So the area to the left of negative 2.53 should be the same as the area to the right of positive 2.53. Now, if I didn't have this information already, what would I have to do? I'd have to go to the table, find the area to the left of 2.53, and then subtract it from 1. So I can prove this, that this idea of being symmetric, folding on top of itself, that those values would be the same. Because when I go to the table and I look up positive 2.53, now here's my 0.3 column. This is why kind of using the table to show you is kind of a pain. So 2.53. The probability that I'm to the left of that is 0.9943, okay? So this is 0.9943. So if I want the area to the right, 1 minus 0.9943, which, lo and behold, is 0.0057, right? Now I can go ahead and do that, but if I already had this information, knowing it's symmetric makes it a lot easier to find the probability that I'm greater than that same value, but positive, okay? Any questions on that? Is that making sense? Let's see if there's nothing, make sure there's nothing in the chat. Okay. So there's no questions on that. Go back here. So, what we're going to do on Monday, I have a couple more things I'll go through, but what we're going to do on Monday is take a variable x that has a mean and a variance that aren't 0 and 1. We're then going to start converting values into z-scores and using that table to find the probability not of just being less than or greater than values, but maybe in between two values or less than one value greater than another. We'll go through a bunch of different types of examples where we're converting a variable x into a z-score and then using this table. So hopefully today we kind of got a good setup of how we use that table, kind of a roadmap of where we're going, what these z-scores mean. But I had a couple things I was gonna show you because I thought they were kind of interesting. So I had this huge survey data. It was like 12,000 people. And I had their height. And so I put it into a histogram to kind of show like human height. Even I think I actually left men and women in the same one. But I think that they were younger. So these were people who were between 14 and 18. So maybe there wasn't as much difference in height yet, but kind of a nice normal distribution. I'm not into CrossFit a ton, but I saw they put out some stuff once, and this was like some workout they had, and they just plotted kind of how people did. And I thought it was pretty crazy. If we look at kind of men and women's performance, these are really close to like nice normal distributions. Not perfect, but they're pretty damn close, right? Especially the female performance here. So we see it pop up a lot. The other thing I thought was interesting to kind of tie together a lot of stuff that we've done, and also just thinking about when we're looking at data to think a little bit more carefully, right? So if we're thinking about, I had this huge data set of all these powerlifting meets, and so it had like what they deadlifted in these meets, their final kind of score. And so obviously, if we look at kind of male and female distributions, they're pretty close to a normal distribution, maybe a little bit skewed to the right here. But you think about like the mean for female deadlift is much lower, right? What, about maybe closer to 300. Here, it looks like it's like 550. Right? But when we think about, we also know that women weigh a lot less. I was thinking about this. I think I read something, I got interested, where it was like, people think about it as like men maybe being stronger is kind of the stereotypical belief. But what's also true is when you look at this data, there's a lot more 300 plus pound men in these powerlifting meets than there are 300 plus pound women, right? So we probably should factor in for weight, right? Well, there's this thing that they actually do in powerlifting for different weight classes, which is called creating a Wilks score, which tries to essentially take how much the person lifted divided by how much they weigh, kind of a per pound strength. So I took that Wilks score, and if we graph that, pretty nice normal distributions here. And notice now if we kind of look at this average, just below 400 for women and actually just below 400 for men. So actually if we factor in kind of per pound body weight, men and women are actually pretty equally, have like equal strength, which I think, is just, I think, an interesting thing to kind of show. We talked about means, we talked about making sure we have the right variable, right? When we're talking about like teachers, we want to factor in per student or something like that. If we're thinking about which states care more about education. Also kind of human performance just ends up being really close to a nice normal distribution, which is just another example that we see this normal distribution pop up all the time, okay? So I'm gonna kind of end it there. Actually, yeah, I'll wait and do that next class. But get that Learn Smart done. If you want to start working on the first few problems on that Connect assignment, I would suggest that. We'll do some Excel work on Monday with the normal distribution. So you can expect an Excel assignment to be assigned either Monday or next Wednesday, depending on how quickly we kind of get through all of it. So you'll have kind of like two assignments running side by side, the Connect and then next week's Excel, okay? All right, if there's no questions, I will see you guys on Monday.